Hello everybody. In this video I want to talk a little bit about acids and bases. This is a big topic and we're going to cover this in a little bit more detail in a following chapter. But first I want to start off by just introducing the simplest case, the Arrhenius acids and bases. So first, what is an acid? So Arrhenius acids are those that release a hydronium ion. It's this H plus right here, and we know that hydrogen is just a single proton with a single electron. So if you take away that electron and make it a positive like this, is just a free proton that when in water can dissociate out and be stabilized. So we can have our generic acid here, H with some other stuff on it that I'm just calling A. We add that to water, it dissociates out into a hydronium ion, and then you're going to have some sort of conjugate anion. Let's take a look at examples of some of the Arrhenius acids. We have hydrochloric acid. We put that in water, we get our free proton, and then we have a Cl- floating around in the water. We can make them out of polyatomics. Here we have nitric acid. We add water, we put it in water, we get our free proton, and we have a free nitrate anion. We can even have organic forms of it, where we're just using carbon and oxygen and hydrogen. This is what's known as formic acid. We put it in water, that hydrogen pops off of this oxygen right here, and we get this free anion right here, which does have resonance to stabilize it. And we get our free proton. A couple of facts about acids: they tend to taste sour. So like lemons and tomatoes and stuff like that that taste sour, that's acid that's in there, usually some form of organic acid. They are corrosive. That means that they will make things rust, but it also means that they can usually burn you and give you like a chemical burn or something like that. And we'll talk about what this means later, but they have a pH that is less than 7. Two different categories of acids are weak acids and strong acids. A strong acid is one that dissociates nearly completely in water. So an example of a strong acid would be like hydrobromic acid. I write out my HBr, I draw a single line going this way, and I have my free proton and my Br-. If I add HBr to water, it being a strong acid is going to dissociate all the way over, and we're going to have these two free species in the water, and we're going to have very little HBr bound together left in the water. Weak acids, however, have a significant portion that does not dissociate in water. We usually write this with this kind of back and forth arrow right here that indicates that we're having a equilibrium between these two states. And we're also going to have a unit where we talk about equilibrium as well in the future. But what this means is that a significant portion will remain as hydrofluoric acid bound together and will not dissociate out into a proton and free F- here. And it's important to note that most organic acids are weak acids. You're still going to have a significant portion that does not dissociate when we put it in water. I also want to mention, people get very confused about this terminology, weak and strong acids and the degree of dissociation. It's important to note that this only refers to how much these acids are dissociating and how much protons they can produce per unit of acid that you add. It does not have anything to do with the chemical or physical properties of the acid. Okay? Hydrofluoric acid, for instance, being a weak acid, can eat through glass. It can eat through human beings, anything. Okay, it has many of the properties you would see in the typical kind of like movie acid. Okay, but it does not dissociate a lot. All right, this hydrobromic also can burn you and do all those things, and that has nothing to do with the fact that it is a strong acid. Those properties are separate from the fact of whether it's a weak acid or a strong acid. Okay, now let's introduce bases. And bases have a lot of the same sort of things as acids here. So an Arrhenius base is one that can release a hydroxide ion. And that's this guy right here. It's a hydrogen bound to an oxygen with a negative charge on it. If I have some generic base here where B could be pretty much anything, it's going to have an OH on it. It's going to produce a cation and an HO minus. Examples here, we have sodium hydroxide. When I add it to water, I get a free sodium ion and a hydroxide ion. Potassium hydroxide, when I add that to water, I get free potassium, free HO minus. Organic Arrhenius bases are pretty uncommon and pretty exotic sort of things, so you don't see that very often. A couple of facts about bases: they taste bitter. A lot of foods that taste bitter to you have some bases in them. They are also corrosive. They can tend to make things rust. They are also what they call caustic, and basically caustic means it can attack mucous membranes in your body. So if you breathe this into your lungs, get it into your nose or something like that, it is going to be very unpleasant and or deadly. And they have a pH that is greater than 7. Okay, I now want to introduce for you guys polyprotic acids. These are acids that release more than one hydronium ion per molecule. So let's look at some examples of that. We saw in some previous examples, we had sulfuric acid. This has 2 protons that it can give up, and then its counterbalancing anion is going to be a sulfate with a 2- charge. This is phosphoric acid. It's going to release 3 protons, and its counterbalancing anion is going to be phosphate. We have special names for these, so when it releases 2, we can call it diprotic. When it releases 3, we'll call it triprotic. This here is oxalic acid. This is an example where we have a diprotic acid that is organic, and again, this has like a resonance structure to kind of stabilize it. And we can have polyhydroxy bases where they release more than one hydroxide ion, just like we have polyprotic acids. A couple of examples. They're really not hard to find. They happen all the time. We have calcium hydroxide. This is going to be able to release 2 hydroxide ions. And we have aluminum hydroxide. We can do 3 here. Now I'm going to introduce the idea of the amphiprotic molecules. Okay, so some molecules can act as both an acid and a base. And the classic example is water. Water will actually dissociate in itself, and it will produce a proton and a hydroxide ion. So because it's both producing a proton and a hydroxide, it can act as both a acid and a base. And you'll see that when we get into more sophisticated definitions for acids and bases, it remains that water is amphiprotic. It will always act as both an acid and a base. Now let's move on to neutralization. So when an acid and a base are allowed to react, they neutralize one another. That means that the protons and the hydroxide ions are going to combine to form water. If we take a look at an example down here, we can take sodium hydroxide, add hydrochloric acid to it, and we're going to form water and NaCl. I've written here salt because I want to, this is obviously table salt, but in fact this is some language that's used throughout acid-base chemistry to refer to metals bound to nonmetals, these type of ionic compounds we've been looking at. Sometimes they call them salts, so this could be, you know, potassium bromide, for instance. They would still call it a salt. And the output of any neutralization reaction, the thing that you should be looking for is that it produces both water and some kind of ionic salt. So we actually have a convenient procedure for balancing neutralization reactions. And I want you guys to pay attention to this because this can actually be used to balance other types of reactions as well. And as we saw before, it's not really straightforward balancing reactions, so it's nice when we have some kind of methodology. We can be clever with certain cases. So let's look at the case of phosphoric acid with potassium hydroxide. First thing we're going to do is we're going to write out our dissociations. We've already seen what they are here. We know we're going to have 3 protons produced here and 1 hydroxide here. Now we know that we ultimately need to neutralize these. So that means that we need the same number of hydroxides as we have protons. So what I can do is just like we did before where we had fractional coefficients, is I can multiply each one of these guys by 3. And then we get this set up here where we now have 3 protons here and 3 hydroxides here to neutralize it. And we still have, we've also multiplied these guys by 3 because we have to multiply all of our factors by the same number, or all of our coefficients by the same number when we do that little trick. Now what we're going to do is we're going to add these 2 chemical reactions together. And when you add chemical reactions together, what you're going to do is you're going to write all of the stuff on the left side of both of the arrows to the left side of one arrow, and all of the stuff to the right side of both of these arrows to the right side of that arrow. So when we do that, we get a reaction that looks like this. And then we have all of these little crazy ions hanging out over here. Okay? And we just need to recognize how they're going to fit together. So every proton and hydroxide, those are going to combine together to make water. So we have 3 protons, 3 hydroxides. It's going to make 3 water molecules. Our potassium and our phosphate, that's going to combine together to make our salt. We have 3 potassiums and 1 phosphate. That makes sense because it says a +1 charge and this says a 3- charge. We know we have to neutralize those charges. We get potassium phosphate down here, K3PO4. Let's take a look at one that's going to be a little trickier here. We have sulfuric acid and aluminum hydroxide this time. We write out our equations and we see we have 2 protons here and we have 3 hydroxides here. Now, I can't really multiply this by any number to get me to 3. What I need to do in this case, because this one's kind of tricky, is I need to find the least common multiple between 2 and 3. So the number that has both 2 as a factor and 3 as a factor, that is the smallest. And in that case, this is 6. So I need to multiply all of these by 3 to get 6 here. And I need to multiply all of these by 2 to get 6 here. So let's do that. Then we multiply them all by 3. We get an equation that looks like this. We multiply them all by 2, we get an equation that looks like this. Then we add them together, and we arrive at this long equation I kind of had to jam in here. And again, we have to figure out what we're doing with this side. So we have 6 of these and 6 of these guys. We know those are going to combine together to make us waters. So we wind up with 6 water molecules. We have 2 aluminums and 3 sulfates. So we know that that's going to be Al2, SO4, 3. There. And now we've balanced this guy, which is probably one of the trickiest ones you're ever going to come up against. Now really quickly here, I just want to have a little talk about acid nomenclature when it comes to polyatomics. We talked before and we saw that we have hypoite as a type of polyatomic, ite, ate, and per8, depending on how much oxygen this guy has, and which one is the most common polyatomic. We'll get the 8. When we have the acids, though, we're going to replace any ites with us, and we're going to replace any ates with ic. So let's take a look at an example of an acid series using polyatomics. ClO4 is perchlorate. When we make an acid out of it, it's perchloric acid. We have chlorate. When we make an acid out of it, it's chloric acid. We have chlorite. We make it into an acid, it's chlorous acid. And when we have hypochlorite, we make hypochlorous acid.